All right. So the last one in the group is a little bit messy. This one, I suppose you could say, was something like a challenge question or a bonus question in some previous semesters. Um, a lot of times, also, we'll see that the question 10 in a problem set is the toughest one to work on, and this one definitely fits. Um, One of the unfortunate things that's going to come up here is that we have a lot of units that don't match each other, right? And in fact, we want meters per second in our answer. And at first glance, we don't see seconds anywhere. We do see meters on one part, but centimeters on another one. So again, we've got enough information here to see that it's just going to be messy. Um, so let's start to plug in. Let's see what kinds of things we're dealing with, and maybe that will give us an idea. So here we've got we're looking for a velocity, right? So that means that we're thinking of something that's moving, which means we're dealing with kinetic energy. So let's start with that. Whatever change in kinetic energy we have is going to come from whatever change in potential energy. Now, in this case, it's talking about a spring. So you have a special potential energy that comes from compressing or stretching a spring. Basically, it builds up energy because it wants to go back to its equilibrium position. It's basically its standard length. So let's see what this will do for us. From the kinetic energy standpoint, we've got 1/2 mass times velocity squared. So definitely a formula we've seen before. The potential energy for a spring is new, however. It's on your formula sheet, it's in your book. There are lots of places to find it. We just haven't needed it before. We saw a sort of variation on it in Hooke's law in the different problem set, and we're going to see something come back again later. But this version is new for us. So 1/2, we've got K. Instead of delta L, they switch in this chapter to use X, which is more common anyway. But this is sort of like the delta L that we used before. And then it gets squared. So as I mentioned to you before, a lot of times we're going to see 1/2 something something squared. Here we go. Um, we can't cancel the mass this time because there's not mass on both sides. Technically, we can cancel the 1/2. That's a little better. Um, be careful. Don't get too excited and too far into it. Try to cancel the exponents. You can't square root from here. That's a problem. So we just have to start kind of plugging in from here. Um, if we think about where joules are supposed to come from, we need newtons times meters. So it's a little bit difficult to see where to track. You have to be careful. This thing has newtons and meters are divided, so it's technically there, but in the wrong spot. So if we look at things we can adjust, these centimeters at the end, we can convert to meters. So cm, think of like cents in dollars. It takes 100 centimeters to make a meter. Because the 100's on the bottom, then we get that our x is 0.0879. So we can divide that manually or bump the decimal twice. So that's what we get for that change in length. Okay, and then it's not immediately clear, other than if you plug it in the wrong way, you're going to get stuck. But these grams don't need to go all the way to newtons because it gets combined in the formula. We just need to get to kilograms, right? And so if you notice, this does say m for mass in the equation itself, but a lot of times people get carried away and they try to go all the way into newtons. We don't need that here. Grams are unfortunately not the type of mass that we normally like. So we want to convert to kilograms, which again we can do just sort of in this space. So grams on the bottom to cancel, kilograms on top to be eventually the answer we want. Kilo or K means thousand. And because the thousand's on the bottom, we divide or bump the decimal 3 times. Eventually we find that the mass is 0.32825. Okay, so Yeah, this one took a lot more preparation to get into it than what we normally see. We had conversions and stuff to cancel, a new formula. This one's been a trip so far. We've a bit of a journey to get here. Um, but we can keep going. Um, if we start plugging stuff in now, I'm trying to scratch out the things that have changed so we don't accidentally use them for something else. But the mass 0.32825 kilograms. It says find the velocity. So here v squared is the thing we're looking for. So I'll put v in the square outside the parentheses to keep a better indication of what we're trying to find. So that's equal to the spring constant. So remember K has these ugly units. We've seen that before. But 38.08 newtons per meter. And then x squared, that's this displacement or this change over here, 0.0879 meters and squared. So, man, it's still looking rough, but we're making progress. We're getting somewhere. Believe it or not, this is going to do something. Well, we're going to see if we check the units. We can sort of eyeball them now. These newtons per meter get multiplied by meters and canceled, then you get multiplied by meters again, turn into joules. Then joules divided by kilograms is meters squared and seconds squared. It's hard to track. On this one, you may want to just kind of trust me that the units come out here, but otherwise you get meters squared over seconds squared, take a square root. It's there. You don't get there in a hurry. It's an ugly combination of stuff. With that being said, if we know the units are going to work out, then we can deal with just the leftover numbers. So simplifying a bit on the left-hand side, there's not a whole lot I can do, but on the right-hand side, we can go ahead and multiply these things. Don't forget to multiply that second number twice because it has that exponent. All right, so that's going to be 0.29422, so on. Then now I'm trying to get eventually v, but for right now I can work on v squared. So if I divide by this thing that's in the way in front, I'm a little bit closer to an answer. That's going to give me that v squared is equal to 0.896334 and so on, so on. And then finally, the end of this hideous question, because it really was ugly, is the square root of that. Again, squared to standard. We want to get rid of that exponent. Take a square root. Put that in the calculator because there's no hope of doing that by hand. 0.9467. Very ugly question. A lot of parts to it, a lot going on. Not as obscure as it may initially seem. You may wonder when you would ever care about this and when it would come up. But if you've ever played pinball, a pinball machine, you pull back on the spring and then you let it go and it launches a ball. So that was more or less the reference point from these numbers. So yeah, a lot of advanced physics, as it turns out, goes into pinball.